All right, so we are on chapter 9, section 3, and we're going to talk about chemical equilibria, which we have already talked about. And remember, this is when I was telling you about you had the basketball team, and you could only have so many people on the court, and you could have a different number of people on the bench, but the number of people coming off the bench and onto the court had to equal the number of people leaving the court to go to the bench. Right? That was my analogy with chemical equilibrium. That's what we're going to revisit today. And so we know that some reactions are reversible, right? And that's when we have this equilibrium arrow, where the arrow is going in both directions. And so that means you can go from the reactants to the products, and you can go from the products to the reactants. And so in this example, right, you have ammonia being formed. Here's your product, right? And the reaction can go in reverse. It can reform the nitrogen and the hydrogen gas, right? As long as it's kind of contained, it's possible to do. And so eventually, if you let this reaction go, the rate of formation of ammonia and the rate of reformation of nitrogen and hydrogen are going to become equal. And that balance of rates of reactions is the chemical equilibrium. That's the number of players leaving the court and the number of players coming onto the court. And so we know that there's no net change in the amounts of our reactant and the amount of our product when we are at equilibrium. You have a set number of people on the court, and you have a set number of people on the bench. They can cross, but you still end up with the same number on the court and the same number on the bench. Okay, so there's no net change in the amount. So we can measure the concentrations of our reactants and our products. And we can look at the ratio of those concentrations and express them as an equilibrium constant. And we use the capital K to represent this constant. And that is, the letter K is equal to concentration products over concentration reactants. And so anytime you see this bracket, that's saying molar concentration, right? Moles per liter. That's what it's referring to. So the equilibrium constant is equal to the molar concentration of the products divided by the molar concentration of the reactants, right? And so if there's more than one reactant or product, whoa, that got kind of crazy. You're going to multiply them together. So if you have, for example, this equation right here, ooh, that wasn't very good. I'm trying to erase just what I want to erase. Okay, and what I have is this reversible reaction. I don't know why that symbol didn't want to go. But you have two reactants, A and B, and you have two products, C and D. And now sometimes, these reactions have to be balanced. And so you look at those little a, little b, little c, little d, those are our coefficients. So we're just like pretending, right? So if I were to write an equilibrium expression for this chemical reaction, what I would say is I want my products over my reactants. Okay, so here are my reactants, and here are my products. Okay, so I put C and D on the top, I put A and B on the bottom. And then if they have coefficients, those coefficients become superscripts, right? And so when we write this, the only things that we write are things that are aqueous, or things that are gaseous. But if they're solids and liquids, we don't actually include them because they don't actually change concentration. Right? If it's a solid, it's a solid. If it's a liquid, it's a liquid. It doesn't really change concentration. Okay, so what does it mean? What does K mean? Well, if K is equal to 1, that means that the ratio of products to reactants is 1 to 1. Or another way to say that is our products are equal to our reactants. And that doesn't happen very often. Really, really doesn't happen very often, very rare. If you have a K that is greater than 1, then that is telling you that your ratio of products to reactants, remember it's always ratio of products to reactants. So if K is greater than 1, then that's telling us that we have more products than reactants. Let's say it's 2. What that's telling me is a 2 to 1, or another way to write that is 2 over 1, right? So if you prefer it in a fractional form, you could say K is equal to concentration products over concentration reactants. So I have 2 to 1 for a ratio of products to reactants, right? And that's telling me I have a K greater than 1. If you have a K less than 1, let's say here, K concentration products, concentration reactants. If it's less than 1, then you're going to have something like this, 1/2. What does that equal to? 0.5. Look at that, less than 1, right? So that's telling me that I have more reactants than I have products. So always kind of write out your little fraction and it'll kind of help you. So what happens when we change the environment that a reaction is in? We stress it. We call these things I'm about to explain to you Le Chatelier's principle, right? Sounds very fancy. And so if we apply a stress to the equilibrium, that's going to change the rate of the forward or the reverse reaction to basically offset what you've done and regain equilibrium. So let's say that we add a reactant. So if we add some reactant, if we increase the concentration of reactant, what's going to happen is that the reaction is going to make an adjustment. And the reaction is going to do the opposite. If we increase the reactants, the reaction is going to want to get to equilibrium, get back to the point that it was by decreasing the amount of reactants. Well, how do you decrease the amount of reactants? How do you make this less? Well, you form more products and you shift right. So that's a right shift. Okay, what if we remove a reactant? So here we're going to lower our concentration of our reactant. What's the reaction going to do in response? Well, it wants to do the opposite. It's going to increase the amount of our reactant. How do you increase a reactant? You're going to shift in the opposite direction. So this is going to be a left shift. Okay, so it's just you're either going to shift left or shift right. And that's just getting back to that equilibrium state, getting back to your original state. So you can actually alter the equilibrium of a reaction by changing temperature. So if we know heat is a product of a reaction, then that's going to be an equilibrium. Why? Not an equilibrium. I look at this and it drives me crazy. It is a reversible arrow. I don't know why, it just doesn't like that symbol. Okay, so if heat is produced, so here we see heat as a product. If heat is a product, that is telling us it is exothermic. Okay, so if we add heat, so if we increase our temperature, what are you increasing? What is an increase in temperature? Well, you're actually increasing a product because heat is a product. So that's the same thing as increasing a product. Well, what is the reaction going to do? The reaction wants to do the complete opposite. It wants to decrease the product. So what kind of a shift are we going to have? Well, how do we decrease product? We're going to go this way, right? So if we have an exothermic reaction and we increase the temperature, we're going to shift to the left. What if we do the opposite? What if we decrease the temperature? What if we make it colder? Then that means that we are decreasing the product. So how do we change that? How does the reaction adapt to that? Well, it's going to want to increase the product. How do we increase the product? Now we're going to shift in the opposite direction. Now we're going to shift right. So you just have to think about it in terms of getting back to that original state. What is it going to do? And so if you had an endothermic reaction where heat was over here, you would be doing the opposite. And we'll do some examples of that, right? And you don't have to memorize this table. They give you this table. I'm not going to give you this table, but you don't have to memorize that. You just have to like try it, okay? So let's go do a couple of little problems. Okay, all right, so what is meant by the term reversible reaction? So in this case, this is a reaction that can proceed in the forward and reverse, R-E-V-E-R-S-E, directions. How do we indicate it? We put that double-headed arrow that PowerPoint doesn't like. When does a reversible reaction, that's for class, that's for class. Write an equilibrium constant expression for the following reactions. Okay, so K is equal to concentration of our products over concentration of our reactants. It's kind of like flip-flopped, right? So what are my products? Here are my products. So I'm going to write concentration of H2 times concentration CO2. And then where are my reactants? They're right here. So I have CO, and then I have H2O, okay? And you don't have to write the states of matter for that. All right, B, K is equal to, same thing. We're going to do products over reactants. I don't know why this got scooched over, but these are your products. So what are my products? My products are H3O plus. You do have to include charge, times CH3COO minus. Okay, now where are my reactants? Right here. So over concentration CH3COOH, and then H2O. But what did we say about H2O? H2O is a liquid, so we don't need to put a liquid, so we don't even put it. So let's just erase it, right? So anything that's a solid and anything that is a liquid, we just don't write. Okay. For the following values of K, indicate whether the products or reactants are present in larger amounts. You don't have to memorize it. Just put yourself the note, K is equal to products over reactants, right? So if K is greater than 1, right, what do we know? If my picture's covering that. If K is greater than 1, then we're going to have more products, right? So that means that this number is bigger if it's greater than 1. If K is less than 1, let me do it in a different color. If K is less than 1, we're going to have more, what's on the bottom, reactants, right? Okay, so 1 times 10 to the minus 5th. What is that? 0 point, right? 1, 2, 3, 4. Oh, no, 1. I was going to put a 5. 1, right? 1, 2, 3, 4, 5. Is that greater than 1 or less than 1? That's less than 1. So you're going to have, in this case, you're going to have more reactants, right? So, yeah, that's all they're asking for. More reactants or products. So we're going to have more reactants. In B, this is greater than 1. You're going to have more products. And then in C, oh, this is that really weird case, right? Where in order to equal to 1, right, if you had 50 products, you'd have to have 50 reactants. And that 50 divided by 50 is 1. And that would be K. So they would be equal. So products and reactants are equal to one another, okay? All right, let's see. Oxygen and hydrogen gas can be generated if electrical energy is added through the electrolysis of water. In which direction will our equilibrium shift, right or left, if the following changes occur? I'm going to cheat. I'm going to make myself a little table here, right? And I'm going to say, okay, what's going to happen? This is what we're going to do. This is what the reaction is going to do. And this is going to be my shift. Okay. And it's going to be super easy. If I add O2, well, I got to come over here and I need to find my O2. Here's my O2. So what if I add O2? What am I doing? I am increasing my product. What is the reaction going to do? The opposite. Decrease product. How do I decrease product? I'm going to go away from the product and I'm going to make reactants. So that is going to be a left shift. Okay. B, let me erase this. B, add more electrical energy. In this case, energy right here is a reactant. So we're going to add more reactant. The reaction is going to want to do the opposite and decrease reactant. How do we decrease reactant? By going to the products. That's a right shift. Okay, this is super simple if you follow this step by step. Remove H2. Where's my H2? Here's my H2. I'm going to remove it, so I'm going to decrease it. So if I decrease my H2 is a product, I want to do the opposite. I want to increase product. How do I increase product? I shift this way. So I go left. Okay. Let's see. What do we got left? We're going to add H2O. So if we add H2O, we're going to increase it. So if we increase a reactant, the opposite is going to happen. We're going to decrease a reactant. Okay. How do we decrease a reactant? Make it go to the products. So that is a right shift. It's not so bad if you do that process. Okay. And I think that's good on that one. And I'm going to skip ahead. I'm going to skip ahead to 19.29. All right. After you open a bottle of soda, oh, this is Dr. B's Diet Coke, right? The drink eventually goes flat. Oh, I'm so sad. How can Le Chatelier's principle explain this using the following reaction? Okay, so this is the same thing that you already know. You know this. We talked about this in class, right? When we open the top, O-P-E-N, open the top. What happens when we open the top? CO2, right, goes out into the atmosphere. So in terms of shifting, what's happening? We are actually, if you look at this equation, we're actually losing CO2 to the atmosphere, right? It's no longer in the soda can, we're losing it. So if we decrease CO2, CO2 is a product, right? The reaction will shift to make more, it's the opposite, make more product, right? So you're gonna make more CO2, but then you're gonna lose more CO2, you're gonna make more CO2, lose CO2 until, right, the HCO3 is depleted. It's just gonna keep going and going and going until it's depleted, right? So you already knew that. Isn't that kind of cool? Things you already knew. All right, that's it. Y'all have a great day.